Hello, everyone. I'm going to go ahead and introduce Dr. Michael Walter. So my name is Eva Bay. I'm the Chief of Staff here at Marchick, and I'm excited to introduce him. Dr. Walter earned his BS degree in chemistry from the University of Dayton in 2001, and as an undergraduate worked on conductive polymer syntheses at the Air Force Research Laboratory at Wright-Patterson Air Force Base. He completed an MS degree in 2004 and a PhD degree in 2008 at Portland State University and joined Caltech as a postdoc in 2008. He was an NSF ACCF postdoctoral fellow from 2009 through 2011, studying the electrical characteristics of inorganic semiconductors in contact with conductive polymers. He joined the chemistry faculty as an assistant professor at UNC Charlotte in the fall of 2011. He is also a strong advocate for STEM outreach education and has developed several material science related hands on education kits for high school science teachers and students. So Dr. Walter is going to take it away. If you have any questions during his presentation, feel free to drop them in the Q&A section, or you can raise your hand at the end of their presentation. You can ask your questions live.
Okay, thank you so much. Sorry. Thank you, Eva, for the introduction. And so today I'm going to be talking about an area of research in my lab using thiazolothiazole materials for optical and electronic applications. And again, as Eva said, I'm at UNC Charlotte, and my lab has been kind of in this area of research for about the last 5 to 10 years, and it's really kind of become an important area for us to develop and help train students, and maybe even work with industry on trying to use these materials for a lot of different kinds of challenging luminescence or fluorescence applications. So my next slide here will be on kind of the overview of our group. We work in areas for materials that can be used for light harvesting, such as photovoltaics, conductive polymers. As you heard before, my background is in material science and conductive materials, and also light emissive materials. And part of our work is we're always wanting, high performance, and that means stable, efficient, of course, flexible, and that doesn't just mean mechanically flexible, but actually means flexible in its application. Can it be used for a lot of different challenges? And lastly, is it processable? The processable part really comes in where we believe that organic materials can really make such a huge impact, not just in using materials for as fluorophores or as pharmaceutical agents, but also using these kinds of materials for organic electronics, organic light emitting diodes or dyes or fluorophores for a lot of different kinds of applications. So what is thiazolothiazole? So the next slide will show what this material actually looks like, the structure of it, the molecular structure. And it also kind of gives a rundown on some of our biggest contributions to the field of this particular material since starting about 2017. The three, I guess almost four areas that have really been developed in our lab using these materials for electrochromism. So that's the one down in the lower left there. So a color changing material. For metal organic frameworks, this is a new, really burgeoning area. A lot of people are working in this area. Solvatofluorochromism, that's something I'm going to talk a little bit more about today. Fluorescence imaging and voltage sensing. And lastly, electronic applications. So in the lower right, you can see a material that was used in a device. And at the center is this really interesting bicyclic unit, which is two thiazole rings fused back to back. And those two thiazole rings have two nitrogens and two sulfurs on it. It's an aromatic bridge, which gives it a specific stability, and it's very planar. So the next slide, we'll see how this material is made, and it's actually a simple single synthetic step. reaction between the benzaldehyde group you can see, or the aromatic aldehyde, and a material called dithioxamide. It's a condensation reaction and an oxidation reaction, so it's a two-step reaction. And once we heat this up, this material forms. It typically precipitates out, and we can access it pretty straightforward. It's a pretty straightforward reaction. And the materials are brightly colored solids. And you can see the bottom there, you'll see the yellow solids, and then to the right, you'll see these very bright emissive fluorescent compounds. And the fully cyclized final product on the right side of the screen there, you see, has these two 5-membered rings that has a sulfur and a nitrogen. And those are the key to this whole area of research, is that bridging unit. It is thermooxidatively quite stable. You can see there are actually no carbon and hydrogen bonds in that center piece. So it holds the two sides of the molecule together, and it also allows for good electronic communication from one side of the molecule to the other. And that is also important for utilizing these for different kinds of applications. So on the next slide, I'll show you our first area of research in this, which was actually an area called thiazolothiazole viologens. So on the next slide, you'll see this compound here. This is the first one we reported on. And it was actually an interesting structure. And what we're actually seeing here is an image of the crystal structure. So this is, these are single crystals that were grown, and we're using equipment to actually understand the planarity of the compound. So this particular compound has 2 rings on either side of it, and it's quite planar. So the point of this slide is really just to show that this particular molecule, the thiazolothiazole, induces a high degree of planarity across the molecule. And so that's quite important. This is much more planar than other materials that are kind of similar structures. So you can see the picture that was taken of those crystals that were grown. They grow quite readily. So these molecules like to organize and stack easily. So this was actually some crystals just grown from a solution of this material. And these are bright fluorescent compounds. And we found some interesting electrical properties of this material as well. So on the next slide, you'll see some of the interesting photophysical and electrochemical properties. Slide 7. The first thing we noticed about them is the really bright fluorescence. And the quantum yields were very high. So quantum yield just means photons in, photons out. Like, how much fluorescence can we get when we excite this molecule? And the quantum yields were very high, over 90%. As you can see, the bright blue emission there in the spectrum. And on the next slide, you can also see that we saw a degree of electrochromism, which means that they change colors depending on their redox state. So when you reduce this particular compound, it goes from a clear yellow to a dark blue solution. And that was reported in that first paper you can see referenced at the bottom of this slide, that we had a very high fluorescence quantum yield, very high fluorescent material, and also it was switchable so that we could reduce it. It could go from clear to dark blue, and that fluorescence color could also change. So on the next slide, slide 9, we'll see that what we're going to transition into now, just spend a few minutes with, is another area of research that has also blossomed and really grown in our group. And that is the area of making thiazolothiazole dyes that are asymmetric. So if you remember before, there was the same units on either side of the bridging thiazolothiazole core, the TTZ core we call it. And in this case, we have 2 different groups on either side. And this, we devised this plan for a couple of reasons. One was that we're wanting to make a dye that has electron-rich and electron-poor groups on either side. So what we create is something called a push-pull mechanism. And in this case, if you see the dye in the box below, all these nice, pretty colors, fluorescent colors of solutions. On the left side of the screen, you see a dibutylaminophenols. So the amine, the nitrogen with these long alkyl chains sticking off the side, and then on the other side is a pyridine ring. This sets up a push-pull effect. The amine side pushes electron density to the pyridyl side. It's an acceptor. And what this does is it changes the excited state of the molecule. Changes the dynamics of the excited state, really. So that when you put this molecule in different environmental conditions, the fluorescence shifts dramatically. And so what we have up there is a slide with a picture of all these different cuvettes, and it's the same molecule, but in different solvents with different polarities. So you see on the far left, you see hexanes, which is a very nonpolar solvent, all the way to methanol, which is a very polar solvent. And these images are taken with exciting the molecule with about a 390 nanometer light, so kind of like a blue light, kind of almost like a black light. And so the fluorescence we get out of all of that, it shifts dramatically, almost across the full visible spectrum from blue nearly to kind of an orange-red in methanol. And we saw that for a few different of these derivatives. So we can put two different groups on either side. So we call these asymmetric TTZs. Because we have a push on one side and a pull on the other. And you can see there's a bunch of pictures here of these compounds in different solvents with different polarities. And we found that the shift in the absorbance versus the emission was some of the largest ever reported. Okay, so on the next slide, slide 10, you'll see how we made these. So before we used two different of the same groups to do the condensation to make a symmetric material. Here we're using two different groups, and we end up getting three different compounds. So in the early days when we were doing this, there's a picture of Nick Sayer-Smith, who's now Dr. Nick Sayer-Smith, who graduated in 2021. He was the first to work on this area, and we realized that when we ran this reaction, of course, we're going to get a mixture. And so we do have to do some chromatography to separate the one compound out, the middle compound. But what was interesting is that middle compound, not only did it show the solvatofluorochromism, the other compounds don't, it also has the highest fluorescent quantum yield. So these are very, very bright solids, bright materials in solution. In fact, the fluorescent quantum yields were almost above 90%. They change a little bit depending on what solvent they're in. So on the next slide, slide 11, we'll see that there's a little bit more information about this whole push-pull mechanism. And what it is we actually calculated what's called the change in the excited state dipole, or the transition dipole. What's the amount that the ground state is different from the excited state? And I won't get into this equation right now and go through it, but what I will say is we are able to take how far the fluorescence changes, what its shift is, and calculate how strong that excited state dipole. And we were getting numbers up to 18 dBi, which is very high for just a small molecule probe, one of the highest ever reported. And so we're very excited about that. So the next part was, okay, well, now that we know it has this strong dipole, what else can we do besides look at different pretty colors in the solid state and in solution? On the next slide, one of the first things we noticed was we could actually use this as a thermometer. So on slide 13, you'll see temperature sensing. In a particular solvent, if you can go to slide 13 there, in the solvent, you can see that the emission changes depending on the temperature. Oh, just one back, sorry. To slide 13, you can see that the temperature changes, the fluorescence changes depending on the solvent. So this particular solvent so it's just one solvent. We're not using different solvents, but when we cool it or heat it up, the solvent that surrounds the dye changes its orientation depending on temperature, and that change the fluorophore can pick up. It's not as dramatic. You can see the color changes blue to orange, but it's visibly different by eye. So you can definitely use this as sort of a thermochromic sensor, I guess. So that was one of the first things we kind of noticed about these materials. But then we decided to branch out a little bit and actually go into an area of research that was quite new for me, and that's on slide 14. And we did have to collaborate with someone at the University of Chicago. So in slide 14, you'll see our collaborator who helped us use these as a cell membrane voltage sensor. This is Professor Yamuna Krishnan, who's in the Department of Chemistry at the University of Chicago. And she helped us realize that we could use these asymmetric dyes to stain cells and not just look at the cells under a microscope, but we could actually do some electrophysiology experiments with them to see how the fluorescence changes depending on the voltage. And so what we have here are two images here on a publication. And on the left, we have some HEK cells in her lab, and we stain them. You can see the outline of the cell. So we're staining just the very thin cell membrane, the phospholipid bilayer membrane of the cell. And the particular structure that we have there, that dye that we've been talking about, is such that it fits down in the membrane and just stains the cell membrane. And we saw that that was a very stable stain. It stayed just on the cell membrane. And after 130 minutes there, it doesn't move around much. So that was exciting. I mean, even just as a biological stain, that we can use this material to image cells under the microscope using a confocal or a regular microscope, light microscope. That was exciting. But what was even more exciting was the fact that we could use these as voltage sensors. So we can actually measure or look at fluorescence changes depending on the cell membrane voltage. So on the next slide there, we'll see how this kind of works. On slide 15, so here's just a cartoon of a cell membrane, right? And we have the inside, the outside of the cell, and the dyes are going to stick down vertically in that membrane. And depending on the polarization or hyperpolarization of the cell membrane, which we do with electrophysiology, we can actually see a change in the fluorescence. And we saw almost about a 10% change per 100 millivolts for this particular dye, which was encouraging, not as high as some of the best dyes. But what was really great was that our system, we knew it was stable. We could image it for a much longer period of time before there was any sign of photobleaching. And we believe that's due to that stable TTZ inner core. So that was an exciting result. Lastly, part C there, you can see that the dye had low cytotoxicity. So once we stain the cells, we're not, significantly, killing cells off as we're imaging them, as we're doing experiments with them. And so that kind of wraps up that part, this part of the talk. Let me just go to slide 16. I'll kind of conclude the overview here. So these thiazolothiazole dyes, they're really multifunctional. We're seeing a lot of different applications. I focused a lot today on the asymmetric ones. We're seeing some interesting solvatofluorochromic effects. We can embed them in different materials like cell membranes and see changes in their fluorescence depending on function of the cell. So this could be used for a lot of different applications, for looking at therapeutic or even like diagnostic applications, seeing the health of cells. It could also be used for imaging. We're also curious about other kinds of applications. We believe these are multifunctional dyes. These thiazolothiazoles really have been focused on, just in like the last 5 to 10 years, a lot more research groups are kind of studying the dyes and how they can be used for different applications. And I think it's, the ease of synthesis, the planarity of the structure, the electronic characteristics, and the optical characteristics are all, they're advantageous and they're very attractive to be used for a lot of different applications. So hopefully today you kind of got a feel for what TTZ is all about. I do want to thank my final slide here, slide 17, if you want to go ahead. Just thank my group. And we had lots of students kind of work on this over the last 5 years or so. And, we're excited that so many students have gotten to work on these materials, and also thank the agencies that have funded us over the years, getting this work moving ahead. And I want to thank Margic and others for the opportunity of presenting, and I'd be glad to take any questions.
Thank you, Dr. Walter. That was really interesting. So as I said before, if you have any questions, you can put them in the Q&A or also raise your hand and I can call on you that way. So I have a couple questions actually. So how does the fluorescence intensity and stability compare with other available probes?
Well, like I think I said, there are many dyes out there. I mean, there's a wide variety of compounds. What we're finding initially is that um, imaging or looking at these materials, their fluorescence over long periods of time, is quite better. I mean, it's much more stable. We're seeing that we're able to image and view these materials either embedded in something or maybe in a cell membrane, and we're able to see that the photooxidation is decreased quite a bit. Now, we have not compared our system to all of the hundreds of available fluorescent molecules out there. But some of the state-of-the-art, for instance, biological probes, we seem to do better. And that's exciting. And I think that's, again, due to the stability of the TTZ core. It has a high thermooxidative stable core that's kind of holding the molecule together. So that's where we think we have an advantage maybe over other similar probes. Because there are many different fluorescent probes that are also have high quantum yields that can be used in a lot of different applications.
Interesting. Thank you. My other question is, what other biological applications can you envision with the asymmetric dyes?
Well, I think that's where we're just scratching the surface right now. We can imagine tagging proteins or putting these in lipids and any kind of biological sensing application, doing FRET with another dye. We've just started looking at putting these in cell membranes, but well, if you do a quick search and look out there, you'll see that fluorescent probes they're used everywhere. I mean, they're used in so much of in vitro work, not just cells, but organelles staining different parts of the cell. Right now, we're just doing the cell membrane, but there's also protein labeling and other kind of sensing work. There's pretty much a fluorophore for almost every many diagnostic tests. Also work with nucleobases or DNA or RNA. So yeah, we think there's a lot of possibilities that we might be able to use our systems, and a lot of for especially biomaterials.
Okay, thank you. And my last question is, how does the fluorescence change when the dyes are embedded in synthetic or natural materials?
Well, that's a great question, because we're finding that as we're putting these into different kinds of materials, obviously they're so sensitive to their surrounding environments. For instance, when we first put it in the cell membrane, we noticed that the polarity of the cell membrane, well, it took on a similar emissive color as certain non-polar solvents. So it's not a very polar environment, although the outside of the membrane is quite a bit more polar. So there's two things going on there. There is actually the polarity of the environment, but then there's also what is, how the structure of the molecule, how it's twisting, what conformational constraints are being put on the molecule. And we're seeing slightly higher quantum yields in different kinds of materials. So that's kind of an interesting attribute, that it's not only the polarity, but also structurally, we might be also changing the emissive nature of the dye. So that you can imagine, structurally, there's probably lots of, interesting areas that we can probe where the dye could fit in a particular pocket of this, a small space or whatever, and that might also adjust that fluorescence. And that's just really due to the rigidity of the system. So that's kind of an exciting area too.
Okay, thank you. We have some questions coming in from the Q&A. Dr. Yogesh asked, these planar molecules seem interesting. You mentioned about their diagnostic applications. Could you please throw more light on emission maxima and how these wavelengths will help with biological purpose?
Well, what's kind of interesting is that we do find that in non-polar, again, we're just starting on this. So in terms of diagnostic, we're not quite yet there. We're really still back at the fundamental photophysics and just trying to understand the structure property relationships. But we're interested. We're reading the literature. We're trying to understand other areas where this could be used to, to maybe diagnose things. But what I think is interesting is that we find that, for instance, when we do the cell work, when you're staining cells, you obviously have to, dissolve this up in buffers or materials and then introduce that stain to whatever you're staining. So we're just doing a stain. And the fluorescence in the buffer solution is very low because the solubility, changes quite a bit. But once the dye goes in the membrane, suddenly the fluorescence is very bright. So when we're doing imaging, the background fluorescence, what I'm trying to get to is that we have very low noise. The background is so low. All we see is that bright membrane, the phospholipid membrane. So we think that is an advantage over a lot of other systems, maybe more water-soluble dyes. This dye is really turning on once it gets into position.
Great, thank you. Kevin Boyle asked, what are some advantages of using TTZs in electrochromic devices over more traditional electrochromic materials? And just a heads up, it will be a hard stop in 3 minutes.
Okay. So yeah, great question. I think right now we're seeing with the electrochromic applications, it's all about the environment of whatever material that it's in. There's a variety of electrochromic materials out there. With our material, we're also seeing the ability of the fluorescence to also be modulated. Not many materials have that same aspect where they can fluoresce when they're in this state, and then when we turn them off, the fluorescence is gone. I think I mentioned that earlier. It acts like a little molecular switch. So it's not only electrochromic, but also electrofluorochromic.
Very interesting. And then Adam Earnhardt asked, in the temperature sensing slide, it appeared there was a stark blue shift after reaching about negative 130 degrees C. What was this due to the solvent freezing or some other cause?
It was actually just the solvent freezing. I'm glad you picked that out. Yeah, so we'll see a change all the way right before the solvent turns into a glass, and then it switches back, and now we're totally restricting any kind of movement of solvent around the system. That's right, yeah.
Great. Well, it looks like that's all our questions. Thank you so much again for
Thank
being
you.
here. I really appreciate it.
Sure, thank you. It was great.
And this recording will be posted on our YouTube channel if anybody wants to go back and review anything. Thank you so much. Have a great rest of your day, everyone.